linear algebra time. Dimension. This is my cheering squad. It's Pablo the Penguin. Okay, so currently we've got the theorem that all bases of a vector space have the same length. And because they have the same length, that number is called the dimension. Okay, here's a weird example. So let's say you have a polynomial of degree m, so polynomial sub m of f, right? That polynomial has a basis of 1, we're using the variable z, so 1z, z squared, z cubed, all the way to whatever degree the polynomial is, so z to the m, right? And every linear combination of that is the set of all polynomials of that degree, right? So because that basis has z to the m, which is m vectors in that list plus 1, then the dimension of a polynomial of degree m is m plus 1. Okay, so this next theorem says if you want to check that a list of vectors is a basis for a vector space, all you need to do is check that it's linearly independent, given that the dimension is correct. I think I can do the proof for that real quick, just hand wavy, but it's essentially from my notes. The reason for this is because every linearly independent list can be extended to become a basis. We learned that theorem in 2b, I believe. So following from that fact, if we have a list where the dimension is correct, then if that can be extended to become a basis, but it already has the right number of elements to be a basis, you don't need to extend it, so you don't need to add any elements, so it can be a basis by that theorem. So if you check that it's linearly independent, then it's already a basis, because it doesn't need to be extended because the dimension is already correct. That's essentially what that theorem is saying. Yeah, so that saves us time, so then we don't have to check that it spans whatever vector space we're trying to prove that it's a basis of. Okay, so here's the third theorem. This theorem states that a spanning list, if it already spans the vector space, it's a basis if its dimension is correct. Sorry, if the number of elements in that list equals the dimension of your vector space already, then you can just say it is a basis. Okay, and let's go over the proof for that one. So the reason why that works is extremely similar to the previous one, the previous theorem. So here we have a spanning list, and we know that it spans that vector space. If we go to the previous chapter, there was a theorem that said every spanning list can be reduced to become a basis. But if our spanning list already has the number of elements in the dimension, then it must be the basis of that vector space. Another way of saying that with a hopefully better camera angle here is every spanning list can be reduced to be a basis for a vector space. And since our spanning list already has the number of elements required, which is the dimension of the vector space, it cannot be reduced any further. And we know that the dimension of a vector space is constant. so therefore it must be a basis. Then finally, we have the dimension of a sum of subspaces. There's a formula, it's just the dimension of subspace 1 plus the dimension of subspace 2. But then you've counted stuff twice, so you subtract the dimension of the intersection of the subspaces. And that is 2C dimension. Very cool chapter. Our exercises for this week will be 1, 4, 8, 12, and 16 from 2C dimension, and I'm looking forward to them. And those are the notes for 2C.